Let's talk about mathematical statements. These statements are the statements that can be either true or false, not both. So we can assign two values to each statement. After that, we said, hey, now that we have statements, let us combine them together and create some new statements, more complex or compound statements. Well, to form compound statements, we need some connectors, we need some operators. We start talking about negation. Negation. It's not the case that different notation that we're using. Some programming languages, they're using exclamation mark as well. But in logical books, you'll be seeing these two notations for negation. Then we have or and implication and biconditional statement. Biconditional, if and only if. So this is if, then, and biconditional, it means that your hypothesis implies your conclusion, and also your conclusion implies your hypothesis. Very well. He said that to make sure it's easy for us to follow the truth or falseness of these compound statements, we introduce truth tables. Truth tables. For negation, it was very easy. We have statement like P and its negation not P. The statement can be true or it can be false. If the statement is true, its negation is going to be false. If the statement is false, its negation is going to be true. Then we talked about or and. For or, we have two statements. So we have four different combinations of their values. P, Q, and the compound statement, P or Q. Well, true, 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 false, false, true, false, false. And we know that for or, it is false if and only if both statements are false at the same time. So it's going to be false, and in other cases, it's going to be true. Well, we talked about and. Again, we have two statements, so it's going to be four combinations. P, Q, P and Q, true, true, false, false, true, false, true, false. It's going to be true if and only if both of the statements are true. So it is true, and for the rest of them, it's going to be false. We talked about implication. If then, if you get 90% on the exam, I'll give you an A. We discussed that. And this was the table for implication. P, Q, P, then Q. True, true, false, false, true, false, true, false. It's going to be false when your hypothesis is true, but the conclusion is false. It means that I lied. False. And for all other cases, it's going to be true. And for biconditional statement, we know that the biconditional statement is true if and only if both of the statements have the exact same value. P, Q, P, if and only if Q, true, true, false, false, true, false, true, false. So true, then true, true, false, if and only if false, true, and the rest of them are false. So again, to keep track of the truthness or falsity of these compound statements, we use truth tables. But eventually, we're going to use some laws to help us identify the truth or falsity of statements. Very well, before moving on to laws for equivalence statements, we're going to talk about De Morgan's laws. So I expect you to ask, can I distribute negation into a compound statement? These are the questions that you should be asking. Well, question. Not P and Q. If I distribute negation over and, this guy is the same as which one of these statements? Is this the same as not P and not Q, or is this the same as not P or not Q? What if I distribute negation over or? The negation of P or Q is equal to, so let's just write down question mark on top of this, is equal to not P or not Q, or is this equal to not P and not Q? Or what if I distribute the negation over implication? Well, is this guy equal to not P, then not Q? These are the questions that you should be asking. What if I distribute negation, not, this is not the case that, and this is not the case that, or this is not the case that implication. So to make sure these are actually equivalent to each other, you're going to construct their truth tables. If they have the exact same truth tables, the validity of the last column is the same, then we have equality, or in this case, we say that we have equivalence statements. Okay, let's take a look at this. So what are we going to do? Since we have two statements, we're going to have 4 combinations. Let us construct the truth tables if their values are the same, outcome values are the same, then we have equivalence statements. So I'm going to begin working with the negation over and. Negation over and. So here I have P, then I have Q. Okay, remember that when we are talking about compound statements, we consider the quantity inside parentheses. They have to have the value for that quantity. Then we start using the rest of the connector or operators values. So in this case, I'm going to write down the quantity inside parentheses here. I don't have these lines, so I'm not really parallel. Okay. So I'm going to write down P and Q here. Then on the next column, I'm going to have the negation of P and Q. Very well. So I have true, true, false, false, true, false, true, false. Well, P and Q, we know that this guy is true if and only if both of the statements are true. So it is true and the rest of them are false. The negation of this column is going to be false, true, true, true. Well, I'm going to use a different color to make sure that I know what I'm focusing on. This is the column that I'm focusing on. Okay, perfect. On the right-hand side, what I have not P and not Q. So I'm going to add more columns here, and then I'm going to compare the last outcome for this compound statement with this column here in orange. So let's see. I have not P, then I have not Q. Then not P and not Q. And the other one that I'm focusing on is not P or not Q. I want to know if I distribute the negation over and, which one of these are actually the equivalent statement. And not P or not Q. So not P. Not P is the negation of P. Well, it's going to be false, false, true, true. Not Q is the negation of Q, which is going to be false, true, false, true. Well, now I'm going to use these two columns to construct the value for this column. Not P and not Q. It is going to be true if and only if both of them are true, which is this case here. True, false, false, and false. Well, so let me compare this column with this column. Are they the same? Are these two the same? I have false and false, true and false. They are not the same. Not the same. So what's the meaning of that? It means that these two statements are not equivalence statements. This guy is not true. Well, what if I combine not P, not Q using or? Well, I know that or is true, is false. Let's go to the false. False is easier. It's false if and only if both of the statements are false. These two are false, so or is going to be false. For the rest of them, it's going to be true. Well, now check these two out. Are these two the same? False, false. True, true. True, true. True, true. Both of them are the same. Both are the same. What's the meaning of that? It means that if I distribute negation over and, it's going to be the same as the negation of the first statement, the negation of and, which is or, and the negation of the second statement. So not P or not Q. This is one of the laws of De Morgan's. Well, as you all guessed correctly, the negation of or is going to be and. You can form the table and actually verify that. This is not correct, and these two are equal to each other. They're equivalent. It means that you can replace them. If you have a question that it says, hey, I have not P and not Q, you can quickly switch to not, parentheses, P or Q. So as I mentioned, these two are De Morgan's laws. Now, what about this guy? What about if you have the negation of implication? Is this equal to not P then not Q? Well, let us construct truth table. Let's see what do we have. So we're going to have 4 combinations. Then we have our implication, our favorite connector, P, then Q, true, false, true, true. And then it says you have the negation of implication. So we're going to construct the negation of P, then Q, which is just negating this column, false, true, false, and false. So this is our focus on the left-hand side. This is our left-hand side compound statement. So let's use a different color to highlight this column on the left-hand side. Then, well, then we have not P, then not Q. So we need the negation of P, the negation of Q, and the negation of P, then not Q. Well, so let's take a look at P and its negation. It's going to be false, false, true, true. For this guy, it's going to be the negation of Q. So we have false, true, true. Okay, so not P, then not Q. False implies false. You know, this is true. False implies true. This is true. True implies false. False, true implies true is true. Well, take a look at this. If these two columns are the same, then we say that, hey, they are equivalent to each other. Let's check these two columns. These are the columns that we're going to compare. Okay, the very first row, here you have false, and here you have true. So these two are not the same. Are not the same. So it means that they are not equal to each other. So the negation of P then Q is not P then not Q. Well, to find the negation, we can actually write it in 2 different ways. First, we can write P then Q as not P or Q, then negate this. P then Q is equivalent to not P or Q. This is very important. Very, very important. You can construct the truth table and actually see we have the exact same truth values. Since you know that P then Q is equivalent to not P or Q, you can just negate this. The negation of P then Q is the same as the negation of not P or Q. We already learned about the De Morgan's laws. So if I distribute the negation, I'm going to get not P, not P. The negation of or is and the negation of Q. And I simplify not P. It turns out not P is the same as P. So we call this double negations. So it is going to be P and not Q. So not P then Q is the same as P and not Q. Another law for you. P then Q is not P or Q. You can negate this and get the negation of P then Q. So this was the first one. The second one is actually using contrapositive. Second is called contrapositive. It says P then Q is the same as not Q then not P. Sometimes we end up having statements that are always true or always false. The statements that are always true are called tautology, and the statements that are always false are called contradiction. So, definition of tautology. It is a statement that is always true. For example, P or not P. P or not P is always true. Don't believe me? Take a look at the truth table. You have P, not P, P or not P. So here you have true, false. It's going to be just, let me write it the way that it has more space here. False, true, true or false, true, false or true, true. P or not P is always true. We call it tautology. We denote it by T. Well, a statement which is always false is called contradiction. It is a statement is always false. Give us an example. If I switch or into and, I get a statement which is always false. P and not P. So will leave me for the truth statement. P not P, P and not P. True, false, false, true. Then you have and. You remember that for and, it's true if and only if both of them are true. In other cases, it's going to be always false. Always false. So this is a contradiction. Did you know this guy by C? Contradiction. Well, my next question is this. Suppose I ask you to show that these two statements are equivalent statements. P or Q, then R is the same as, guys, sometimes we use equality, sometimes for equivalence we use 3 lines. They have the same meaning. So equivalence, or they are equal to. Equal to P, then R, and Q, then R. Okay. Suppose I ask you to show this. Well, you might say, hey, I have 3 statements, P, Q, R. Since they have 3 statements, they have 2 to the third or 8 combinations. Or you're going to have 8 rows, which is going to be a very huge table. I expect you to ask, do we have other methods proving 2 statements, 2 compound statements are equal to each other? Actually, we do. We have some laws to follow and show that compound statements, more complicated, more complex compound statements are actually equivalent to each other, or they are not equivalent to each other. So these are the important laws that you need to know when you're using them to proving 2 statements are equivalent or they are not equivalent to each other. The very first one is called commutative laws. P and Q is the same as Q and P. The order is not important. We have the same thing when it comes to or. P or Q is the same as Q or P. So this is called commutative laws. The next law is called associative laws. It says, well, the combination of P and Q and R is the same as combination of P and Q and R. So it doesn't matter if you combine P and Q first, then find the value combined with R using and, or first find the value for Q and R, then combine it with P using and. You can group them together. It doesn't matter. The same for or. P or Q, they can combine to each other first, then combine with R, or you can combine Q, R using or, then combine it with P using or. This is called associative laws. Well, as we can distribute negation over and or, we can also distribute and over or, and we can distribute or over and. So if we distribute and over or, it's going to be the combination of P and Q connected with P and R using or. And then if we distribute or over and, it's going to be P or Q and P or R. These two are very important. Sometimes you end up with expanded form like this, and it's much easier to combine them, as you can see on the left-hand side. The same here. If you distribute or over and if you have the expanded form on the right-hand side, it's easier to write it in more compact and precise way. The fourth, identity laws. If you combine P and a tautology, it's always P. If you combine P or contradiction, it's going to be always P. So P and a tautology is P. P or contradiction is also P. So P and tautology is always P. Any tautology works. Suppose you have this. You have P and this tautology. P or not P. Or it can be anything. Suppose you have Q or not Q. If I ask you to simplify this, you say, hey, I already know that Q or not Q is a tautology. So I'm going to just quickly write tautology here. And P and the tautology, the identity law tells me that P and the tautology is P. You might have a contradiction. We know that P or contradiction is always equivalent to P. Any contradiction works here. Suppose you have P or a statement like R and not R. You already know this guy is contradiction. You quickly write, this is always false. This is a contradiction. And I have P or a contradiction. And the identity law tells me that P or a contradiction is always equal to P. So that's why these laws are very important. They help us to actually simplify complicated and complex statements. Very well. More laws. Negation laws. So what if you just combine a statement? It can be any statement. It's negation using or. We already proved this. It's going to be a tautology. It's always true. If you combine a statement, any statement, with its negation using and, it's always false or it is a contradiction. Double negation law. Not P is the same as P. Idempotent laws. Well, what if we combine P and P using and, using or? Well, it happened that both of them are equal to the original statement. Universal bound laws. If we combine P tautology using or, the outcome is always true. It is a tautology. If we combine P with contradiction using and, it's going to be always false. The outcome is a contradiction. We have already talked about De Morgan's laws. If we distribute negation over and, then the outcome is the negation of the statements, and the negation of and is going to be or. Well, if we distribute negation over or, it's going to be the negation of those statements, and the negation of or is and. Two important laws, absorption laws. If we combine P with P and Q using or, the outcome is the same as P. And if we combine P and P or a statement like Q, it doesn't matter what Q is, then the whole compound statement on the left-hand side is the same as P. And finally, the negation of tautology and contradiction. As you all guessed, the negation of tautology is contradiction, and the negation of contradiction is tautology. There you go. Let's go over our example. So how do I show that? Know that here on the left-hand side, you have a compound statement. So I'm going to write down as left-hand side. And on the other side, on the right-hand side, I'm going to copy this guy down as right-hand side. So right-hand side and left-hand side. Left and side. So what I'm going to do, I'm going to start from either left-hand side or from right-hand side and get to the other side. So I'm going to write the right-hand side and get to the left-hand side. Well, my right-hand side is written as P, then R, and Q, then R. There you go. So you're going to write it this way. We know that P, then Q, or in general, you can switch to A and B if you see it gets confusing. A, then B, is equivalent to not A or B. So in general, if you have hypothesis, then conclusion is equivalent to the negation of hypothesis or conclusion. So this guy is not P or R and not Q or R. Very well. So what do we have here? We are distributing something over something else. We're using one of the laws. Which law is this? Which law is this? How can I write this expanded form into compact and nice? This is written in expanded form. If I take this and write it as not P and not Q or R, it means that I'm distributing or over and from right hand side. So of course it's distributive law. The law that we have is distributive law. Here we go. What about this guy into parentheses? How can I rewrite this compound statement? Which law actually helps me to rewrite not P and not Q? So now we're going to use De Morgan's law and we're going to write it as not P or Q. So this is De Morgan's law. Well, so this guy can be written as not that P or Q or R. Well, take a look at this. Here you have not statement. This is statement A or statement B. Not A or B, which can be written as A, then B, which is P or Q, then R, which is our left-hand side. Very well. So let's go over some definitions. Then I have a question for you. Then group activities. Definition. Suppose you have two statements. Let A and B be two statements. We already know that A then B is conditional statement. Implication. A then B is conditional statement or implication. If you get 90% on the final, I give you an A. If you have hypothesis, then you see the conclusion. Well, if you write a conditional statement this way, B, then A, it's called the converse. So if we switch B, A, if you switch conclusion and hypothesis, we have a name for it. We call it the converse. If you write the negation of hypothesis, then the negation of hypothesis, then the negation of conclusion, then we call it inverse. And you already know that if you write the negation of conclusion, then the negation of hypothesis, it's called the contrapositive. It is called the contrapositive. And we know that A, then B is the same as not B, then not A. Now I have a question for you. This is a question that you didn't ask me, and I expected you to ask me. Which one comes first? Remember the order of operations in algebra? Here we have some connectors, some operations. Which one comes first? Negation and or implication by conditional. Which one comes first? If you have a statement including all of these, which one comes first? There you go. Negation takes the priority. After negation, what do you have? So negation takes the priority. The top priority is for negation. After that, does it come and or implication by conditional? Which one? Okay. So after negation, we look at and or. After and or, you have implication and by condition. Okay. Well, so this takes the first priority, second priority, and the third priority. Now here's my question for you. If you have P and Q or R, which one comes first? If you have P, then Q, if and only if R, which one comes first? So, guys, if you see a compound statement like this, this is not legit. It must be either in this form or it must be in this form. We just learned about distributive law. So if you write it this way, P and Q or R, which one is distributed over which? Is it and distributed over or is it or distributed over and? We have no idea. We need to have parentheses. If you see something like this, you stop and you say, hey, I need some grouping symbols. I need parentheses. I need curly brackets. Something that tells me which one needs to be distributed over which. So this is not going to be correct. The same for this. You either have P, then Q, if and only if R, or you have P, then Q, if and only if R. They are not equivalent to each other. So make sure when you see these compound statements, you have all the information to make sure you have a correct final value for these compound statements. It is not from left to right.